In this presentation, I'm going to talk about graph and graph rag, just like the previous presenter. So I'm going to try to provide a different perspective, even though maybe the slides I'm going to show are not at the deepest level of technicality. So I'm going to try to maybe indicate how things can be done with Oracle software and maybe give a hint about our direction. So for background, I'm a research manager at Oracle Labs in Zurich, Switzerland. I work on graph machine learning, recommendation and search, as well as more recently LLM-centered use cases and problems. The slides here that I'm going to present have been mainly done by my colleagues Meli and Marwan. Meli being part of the Oracle Special Graph product group, and Marwan being a member of Oracle Labs in Morocco. Before I proceed, I just want to give you a few seconds to be able to read this, which more or less says that whatever I'm going to present today might be included in products or might not at some point. So please keep that in mind. So maybe contrary to the previous talk, one difference with Oracle is that we are aiming at having a converged database. So in the latest release, 23 AI, we have features that help with dealing with both graph and relational data. So we support graph data, especially by implementing the SQL PGQ standard. So I think there was a talk from my colleague Oscar Van Rest yesterday related to that. So please check it if you're interested about that. In the latest release, we have included a lot of functionalities to make AI workloads easier to operate inside the database. So we have on one side support for vector types and vector indexing to do vector search in the database. And we have also included support for running ONNX models that enable generating vectors among other functionalities. You can run pretty much all ONNX models at this point. And then also just to mention, so besides relational and graph, we support also more unstructured data with JSON. And in the future, you might understand that we're maybe aiming at integrating more capabilities so that everything can be done in the Oracle database. So now I'm just gonna describe RAG briefly for just in case so that we're on the same footing, even though I guess at that point you're pretty familiar with it. So with LLMs, you give a prompt and then you hit generate and then you get an answer. If you set some parameters like temperature and so on, maybe you will get more creative answers or more out of the common path answers. Those LLMs are generally quite big, trained on a lot of data, and they are, of course, quite useful. You can produce very meaningful outputs and useful outputs. But in some cases, maybe LLMs don't generate super accurate outputs representing actual facts. So maybe here, if we just prompt with a basic sentence asking about the OCI generative AI services with which actually this screenshot is done in their playground, we can see that at some point it indicates something that is a hallucination, so not true. So those LLMs, they have a deep knowledge, but sometimes they mess things up a bit and hallucinate a tiny bit, right? So with RAG, in general, the goal is to fix those hallucinations, to be able to have more factual and trustworthy answers. And typically, it's done by adding in the prompt of the LLM more context with content of documents retrieved previously. So this is for more traditional RAG. So if we look at the traditional RAG architecture, we have a database. Usually there's a vector-based retrieval step. So that can be implemented in the Oracle database with the new vector indexing functionalities. The documents that we want to use as a fact database are encoded with some vector embedding model. And then whenever the user query comes, which in the RAG context means either a subpart of the prompt of the entire prompt we will pass to the LLM. Then we trigger a search to find relevant documents. We enhance the prompt to include those facts or those contents of documents. and then the LLMs will provide the answer. For the search part, retrieval, vector-based retrieval is sometimes sufficient. Sometimes it's needed to do a bit more, maybe with some re-ranking or pruning stages afterwards. So here, yeah, you can see just some examples in practice extracted from some paper, showing that based on some query, the different stages can bring us to the right answers in the end. I'm gonna give you some time to have a look. All right, so how can we implement this today with the Oracle offering? So some parts can be done in database, maybe not everything. So here in this example, actually it's using the OCI GenAI service from the OCI offering to get access to a pretty good LLM, the Cohere command model and Cohere embed models to do the RAG part, right? So actually here we show that we have libraries basically that integrates with, let's say, LangChain and others to do the typical RAG. Now today, actually, those slides are a bit old, so we could do, for example, the vector retrieval from the Oracle database instead of from Face. But maybe still at this point, it's probably a good idea to use Cohere command model for the generation part, as it's a pretty good model. And maybe this one in database is a bit challenging to run today. So yeah, as you can see, on the indexing side, on the left part of the code snippet, you can start with just extracting the text content from your PDF, let's say, and then you can embed them with a Cohere embed model, put them in a vector store. So here in your mind, please imagine that it goes to the Oracle database. Then during query time, so we can get a query. Here the question is, does Mac have a direct experience with Java and MapReduce? And then we can retrieve with the vector store. At the part below, you can see how we have a simple prompt that adds the context retrieved from documents. So there's the initial, let's say, system prompt just indicating what the goal is, and then we provide a question, and then the different context, the documents content from for additional context, and then do the final generation to get the final, hopefully more trustworthy answer. So that was the traditional RAG, right? And then now I'm gonna try to talk about graph RAG in general. So yeah, you're pretty familiar with graph data. So you typically can have, like, let's say, knowledge graphs where you connect entities through relationship with edges. And if we're graph RAG in particular, we're trying to extract those interesting facts from arising from different relationships. So your knowledge graph can become quite complicated. You can have a lot of relationships and different entity types. So here we have people that can visit locations, they can use services or products, and then we have even like conferences. So now we might want to add even more facts, right? So for example, relatedness of different conferences, or that specific people use specific things, and that those facts should help us try to answer complicated questions for which we might have had no documents that provided all the facts at once, but by having the graph and all the relationships, we should be able to, let's say, aggregate an answer that's trustworthy. For example, answering who is likely to use the GenAI service. Based on this graph, we could just see, GenAI service is connected to Giant and Marwan. And then yeah, maybe if we want to extend, we could see that Melly, because indirectly she's connected to her colleagues, Melly is probably also likely to use the GenAI service. Right, so the question is, how do we enable this kind of RAG where we can answer complicated facts through navigating relationships in a graph. And that's what next slides are going to try to show. So today, actually, with the Oracle offering, maybe we can aim at implementing such a system by more or less using graph ML models or algorithms. One way, yeah, you could just follow, PageRank style, kind of see what is relevant based on starting nodes. But yeah, more recently, we have introduced graph machine learning models or algorithms that can help with that. They are available today in our products. So DeepWalk was, for example, one of the first graph machining models published, and it's still relevant here because DeepWalk can help learning embeddings on graph vertices, and it will capture closeness in the graph through the topology. And if facts are well connected, it can even help finding close vertices in semantics. There were more recent developments, and for example, we introduced more recently the GraphWise class of algorithms in our offerings, which is kind of related to GraphSage, if you're aware of them. And actually, in this GraphWise family, we can actually generate embeddings for vertices or edges. And very contrary to DeepWalk, it can also consider features or attributes associated to vertices and edges, so that it can actually have more chances to capture semantic similarity besides just topology closeness in the graph through relationships. So those models actually have supervised and unsupervised variants, and the unsupervised variants are particularly appropriate here so that we can learn embeddings without requiring a prior knowledge of what needs to be learned. So if we look more precisely, maybe we can start with DeepWalk. So DeepWalk, as a reminder, just does random walks in the graph, collects the random walks kind of inside, let's say, documents, and then we learn an embedding for this vector, learning to make the embedding of a vertex close to the other vertices that were sampled on those walks. So in our offering, if you want to use the DeepWalk model, it's pretty simple. You more or less need just this code here, and then you will get embeddings for all your vertices in the graph. And those vertices, you can, those embeddings, you can bring them into Oracle DB, for example. Then GraphWise, more recent work, works a tiny bit differently from DeepWalk. So instead of just generating random walks, so kind of like flat list of vertices after vertices being sampled, here it actually looks at neighborhoods of vertices and aggregates information across the neighborhood. So we start from a center vertex, so here in yellow. Then we do some sampling of neighbors and collect them, and then go expand kind of in BFS style to the second hop. So that's the sampling part. Then when we actually do the aggregation part to collect the information from neighbors, we do a bunch of matrix modifications to kind of coalesce the information from the variable number of neighbors towards the inner circle of vertices being sampled until we get to the start vertex that we wanted to generate a vertex for. So again, this model, pretty simple to use with our offering. Here's the difference is you can also specify maybe the vertex features you want to consider for that might be relevant to consider in the embeddings, as well as edge features, which is not shown here. You can train it, especially the unsupervised one, you don't need anything, and then you can get your embeddings. So once we have, let's say, embeddings generated with graph machine learning models, the architecture for RAG can be as follows. So we can still index in a vector database, but what we index is a bit different. We will index the embeddings for the different vertices or edges we have obtained from the graph machine learning model. And yeah, the flow would be still unchanged besides that. So we still get a user query with a prompt, and we will find relevant vertices and edges. So for better results, yeah, it's better if we can have especially, let's say, text features on the vertices or edges so that the user query has a chance to kind of be matched against this kind of text stored as attributes to the vertices and edges. Right. So before we actually see what it could give in more realistic setting, one question is actually, okay, what could it help with if actually we did the ritual part correctly, right? So let's forget about the ritual part. Let's assume it actually works. Does the LLM or can the LLM actually leverage whatever we retrieve to produce better results? So here we showed an example where we prompted the Cohere model with a prompt which varies a bit more, but here it's made shorter because there is no space to show the full prompt. But if we bring facts as a kind of like a list of edges and vertices being collected with the retrieval part, then we can see that in the answer, the model is actually able to kind of aggregate the facts and make coherent output that leverage all the facts presented. So here, to make it work, actually, yeah, we had to show a bit some examples to kind of make the model understand what this format we used here meant. But yeah, after that, it's possible to get good outputs. Right. So more recently, actually, since the slides have been made, there have been quite a lot of interesting research. Maybe some quite interesting ones that would like to highlight is this kind of approach with GRetriever, where actually the LLM and the graph models are kind of made together so that the embeddings from one is kind of usable in the other. And that solves maybe one problem that if we had to implement the solution with what we have today in our products, yeah, it requires a bit of work to actually get the textual embedding to be correlated enough to the vertex or edge embeddings we learned with the GraphWise model. So yes, it helps with improving the overall quality of the retrieval. So it more or less concludes the part about GraphRag. We can discuss more in questions if needed. But besides GraphRag, so LLMs can be used to generate queries. So in this slide, actually, from a few months ago, my colleagues many verified that current LLMs can generate queries, graph queries, for example, SparkRoll queries. We have verified since then, but maybe we don't have slides here, that it actually can work pretty well with the SQL PGQ standard, even though actually I think most of the models we have tried on actually were trained before there was a lot of SQL PGQ material available online and therefore probably ingested during training of those models. So that would conclude my talk. So if you're interested in seeing actually more about our products and on those links, there are actually, especially in the blog parts, there are presentations about how to implement some of the things we outlined here. So the main one is probably the graph database webpage, but there's also the blogs that are quite interesting and show different types of content with more, let's say, hands-on and more targeted per topic write-ups. So that's it. If there are any questions, I would be happy to answer them.
Okay. Any questions? Thanks. So could you just elaborate a little bit more on how you I think you described it as the few-shot learning, how you were able to uh, get the model to understand, let's say, the pattern matching of SQL PGQ, and how easy that was, and how much information did you have to provide for that kind of acquisition of knowledge to occur?
Yeah. So yeah, it was a few shots. So actually, I think for the models we tried, we needed to provide at least two, three kind of examples where we both showed kind of the input question or natural language from users, as well as the output SQL PGQ query. And we had to show, let's say, from simple queries, just doing simple navigational stuff, to more complicated things. So at this point, actually, yeah, we maybe don't have a perfect answer, but for example, to help the model understand how to use more complicated recursive queries, we need to, of course, explain with a few, two, three examples what the recursive things can be and the syntax. But overall, yeah, for simple things, two, three basic examples work. For more complicated things, we need to add
So,
extra examples related to those specific functionalities. Let's say.
so that sounds like it's not that big a deal. I mean, you have to sort of think about it and get good examples and so forth. But do you, and obviously, I guess over time you'd expect that the trainings will imbibe more and more information, so you'll have to do less and less of that. That SQL PGQ will become better understood and so forth. But for the moment,
Mhm.
and I guess in general, for situations where you may be asking these models to do things that are not well understood or not well propagated in terms of of sort of documented knowledge, do you provide copies of the example questions and then the query translations and so forth to your customers so that they can get the same kind of benefit? Because it's almost like that's a mini part of your product to make your product actually work well in this context, if that makes sense.
Yeah.
Do
So
you
actually,
document this? Yeah.
mhm. Yeah. So actually, we do some exploration with some specific customers, and to those specific customers, we kind of provide the exact prompt. But you might imagine that we might do, let's say, an actual solution where we try to make something a bit more generic,
Yeah.
working for the general case, and then what you can imagine that would happen is actually maybe instead of having a fixed prompt with fixed examples, we might have like even RAG to find relevant examples based on what the question seems to require.
So
Um,
follow up on that. Have you thought about? Have you tried things like supplying the SQL PGQ spec or the BNF that's produced as a adjunct, electronic artifact with GQL, but it's the same information. Do you have any experimentation on that kind of level of formal specification information and how that could actually help with this problem? Or
so um, yeah, I think some of my colleagues tried because some of our colleagues are, let's say the formal guys who write the specs, right? So they're interested in that. But I think at this stage we see that providing more targeted examples showing the actual um, SQL queries works a bit better.
yeah.
Um, Probably because, I mean, even online, like those models have seen a lot of SQL, and SQL PGQ, when you look at the actual query, is a lot like SQL, while, just reading a spec is a bit tough maybe for those models. They haven't read a lot of specs, I guess, online.
Yeah, and they'd have to pay ISO to get to read them as well. No, I'm kidding, but yeah, no, that's very interesting. Thank you.